Imagine trying to find a single typo in a library of a million books. That's the kind of challenge engineers face when monitoring complex systems. The constant streams of data from servers, factory machines, or financial markets are like endless novels, and a tiny, hidden glitch can signal a catastrophic failure. Traditionally, spotting these glitches required building a specialized AI for each specific data stream, a process that is both time-consuming and expensive. But what if we could build a single, master AI that has read so many books, it instinctively knows when a word is out of place in any new story it's given? This is the very question at the heart of this new research. The paper introduces an idea that could change the game for anomaly detection, a foundation model for time-series data. You've likely heard of foundation models like GPT, which are trained on vast amounts of internet text to understand language. These researchers want to do the same for the language of data that changes over time. Their proposed model is called FAI, or Foundation Auto-Encoder. So, how does it work? At its core, FAI uses a clever technique based on a generative model called a variational autoencoder, or VAE. Think of a VAE as a combination of an expert artist and a sharp-eyed critic. The model is trained on huge amounts of normal, boring time-series data. It learns to take a sequence of data, compress it into a tiny, essential summary, and then perfectly reconstruct the original sequence from that summary. It gets really good at drawing normal. When this trained model is shown a new piece of data that contains an anomaly, a sudden spike, a weird drop, or an unusual pattern, it struggles. Because it only learned to draw normal, its attempt to reconstruct the weird data is flawed. The difference between the weird original and the flawed reconstruction is called the reconstruction error. A high error is a bright red flag that screams anomaly. To make the model even smarter, the researchers use a technique called dilated convolutions, which helps the AI spot patterns over long periods, like noticing a slow, dangerous buildup of pressure over hours, not just a sudden spike in a second. The team built a proof of concept of FAI and tested it on several challenging datasets, including real operational data from a mobile service provider and the well-known KDD 2021 Anomaly Detection dataset. Their preliminary results are very encouraging, showing that the model could successfully identify anomalies in these datasets, out of the box, without needing to be retrained specifically for them. This is a big deal, demonstrating that a zero-shot, general-purpose anomaly detector is a real possibility. Of course, this is still early work, as the paper's title, Towards, suggests. The biggest challenge ahead is gathering and curating the truly massive and diverse collection of time-series data needed to train a true, all-knowing foundation model. But this research provides a powerful blueprint. It makes you wonder, what could we achieve with a plug-and-play AI that could instantly start monitoring any system for signs of trouble, from a city's power grid to a patient's vital signs? If you enjoyed this breakdown, don't forget to like, comment, and subscribe for more AI research made simple.